Good morning, Year 10. In this video, we are going to begin a new topic, which is graphs. So please make sure that you have a heading for graphs in your book before starting today's content. The first thing we're going to look at is direct and inverse proportion. So because there's two aspects of this, we're going to look at direct first. So you'll see direct proportion is when we have an equation that looks like this. We have y is equal to kx. Now, all that means is that in order for something to happen, we have to have something else multiplied by what is k. And k is a constant. I like to call it a KFC constant because it starts with a k. Yeah, it's just a constant number that's always being multiplied by x. So one common thing that involves direct proportion is getting paid. So if you have a part-time job, or if you know someone that does, if you're working a wage, which means that you get paid per hour, this works very similarly to working per hour. So x would be the number of hours worked, and k, the constant, would be how much money you'd earn per hour. So let's say you earned $10 an hour, and you work 3 hours, you'd get $30. So 3 hours gives you $30, and it will constantly increase. So if you worked 5 hours, you get $50, that type of thing. So for our first example, we're going to look at how direct proportion can work and apply it to some parts here. So for the first example, the distance d in meters travelled by a car is directly proportional to the number of rotations r of its tyres. After 540 rotations, a distance of 950 meters is travelled. Okay, so because we have here, you'll see I'll highlight it, it says directly proportional. That means that we're involving a formula that involves y equals kx. Now you'll see it doesn't have y and x, instead it's got d and r. Okay, so when they say the distance is directly proportional to the number of rotations, that means we're saying that the distance is equal to k times r. Okay, so we've got our general form here, and then this is specific for this question. Okay, and the reason why that's important is because we need to be able to calculate what k is. The reason being is we've got given information for one specific situation, which is this many rotations is this much in distance. But now it says what distance to the nearest meter will be travelled after 800 rotations. So we need to know what k is so we can figure that out. So my first step after getting the formula is to substitute values in. Okay. So I'm going to sub in, d is equal to 950 and r is equal to 540. Okay, so if I do that, I'm going to have an equation, 950 is equal to k lots of 540. So I'm just going to write it like that. Okay, now I want to know what k is. So if I divide both sides by 540, I'll know what k is. So I'm going to do that now. Divide both sides by 540. And you'll see I'm going to move k to the left-hand side. And then I'm just going to rewrite the left-hand side on the right, which was 950. But now I've divided it by 540. Now if you type that into your calculator, so if I type in 950 over 540, I get 1.759, and then things start to repeat. Okay, I don't want to write something like that because it gets a lot long and messy. I'm just going to simplify the fraction to be 95 over 54. Okay, and that's what my k value will be. All right, I'm just going to shrink that so that we've got more room, and we'll keep going. So now we know what k is. That was the purpose of all that. Okay, so now that I have k, I can now find the distance after 800 rotations. Okay, so I'm going to start the next bit by saying when R is equal to 800, because that's what we care about at the moment, distance will equal, now K, which we just found was 95 over 54, and we can multiply that by 800 because that's what R is. Then we'll type that into our calculator. And this time I will go to the nearest meter because that's what it asked for, but I'm going to write it to a couple decimal places first. So my distance is equal to 1407.407, so on. So my answer, which I'll write on the left here, my distance is 1,407 meters. Okay. So this might feel a bit weird at first, but basically the steps are rewrite the equation, find what K is. Once you have K, you can then do whatever you need to with the equation. In this case, we needed to find the distance. The next thing we'll see is how many full rotations will be needed to cover 360 kilometers. Okay, so this time we have the value for D. Okay, so I'm going to, first of all, write that the distance is 360 kilometers. But you'll notice a problem, and that is, if I go back to the question, it says the distance is meant to be in meters, not kilometers. Okay, so because of that, I need to change the units. So I need to change from kilometers to meters. Okay, now there are 1,000 meters per kilometer, so I just need to multiply my distance in kilometers by 1,000. So if I do that, I'm going to get 360,000 meters. Now that I have that, I'll be able to put it into the equation and solve. So remember the equation was distance is equal to KR, which we created up here. So now that I have that, I'm going to rewrite the equation with the information I have. So I've got 360,000, and that's equal to K, and K we found out before was 95 over 54, and we times that by R. So if we want to get R by itself, because remember this is being times or multiplied, I can divide both sides by 95 on 54. Okay, and that will get rid of the fraction. So I'll do that now. I'll divide both sides by that. So I'll type in 360 and then 3 more zeros after that. Divided by 95 over 54. And I get R is equal to, so I'm just going to rewrite what's in the calculator, 204,631.5789. That's what I got in the calculator. And it says how many full rotations. So that means we only care about to the nearest rotation, because that's how many full rotations there are. I guess it's not the nearest rotation, because this is only part of a rotation. So we basically can just ignore the decimal places here. So it's not really a rounding question. It's a bit different. So the number of full rotations is 204,631, which is quite a lot of rotations actually. But I guess 360 kilometers is pretty far. All right, so that's going through direct proportion. And what direct proportion really means, as I said before, is however many of this happens, it always increases by K every single time. Just whenever you're unsure, just think about money. It always works better when you think about money. Next, inverse proportion. Inverse proportion is very similar to direct proportion, except it's the inverse. And remember, inverse is kind of like the reciprocal, as in like we flipped it. So instead of it being K times X, it's K divided by X, okay? So K divided by X there. So in the way that we were thinking about money before, it doesn't work as well to think about it like this way, because money, like getting paid, is an inverse proportion. But basically, like as x increases, y decreases, where before it was they were both increasing together. I think it'll be better if we just go straight to an example. So for inverse proportion, we've got our second example here. The time t in minutes taken by a car to travel 100 kilometers is inversely proportional to the speed s in kilometers per hour of the car, as shown in the table below, which is here. At 50 kilometers an hour, the time taken is 120 minutes. So here's the 50 kilometers an hour, 120 minutes. Okay, I will just quickly add up here, this is example 2, because I didn't include it at the beginning. Okay, so the first part, find the inverse variation equation for t. Okay, now that is basically the exact same thing as what we were asked before, except now it's the inverse proportion. So normally it would be y is equal to k on x. But you'll notice, but so far we haven't used y and x, we've used different things, and that's because we're doing real life applications of these things. So I'll still write y is equal to k on x, but I'll immediately change it to the values that are relevant for this. So instead of it being y, I'm going to do t. So the time is equal to k over s. Okay, the reason why I know that is because it's saying time is inversely proportional to the speed. So whatever comes first is the thing by itself, and whatever's proportional to is the thing that goes with the k. So we've got t is equal to k on s. Now it says find the inverse variation equation, so all we now need to find is k. So that's what this is saying. It's just telling us, hey, what's the equation? Well, we've got an equation, but it's not the one for this situation. So now we need to put some things in. I'm going to use this here, 50 kilometers an hour, 120 minutes. Okay, so I'll just write here, when t, so the time is 120 minutes, s, so the speed is 50 kilometers an hour. So I'm going to have 120 is equal to k on 50. Now I want to have k by itself, and we've got currently k divided by 50. So I'm going to divide times both sides by 50, and 120 times by 50 is 6,000. I always like to double check in the calculator. That's what k is equal to. So if k is 6,000, we can then rewrite the equation time is equal to 6,000 over s. And that's just for this question, okay? So you can see, even though the heading, the topic of that we're doing is graphs, we need to be able to manipulate the equations that we're using for the graphs. So we won't even get into graphs today. We'll just be getting into the manipulation. So part B says, how long did the car take to travel 100 kilometers? And then we've got 40 kilometers an hour and 110 kilometers an hour. So we're just going to apply the formula that we've got right here. Time is equal to 6,000 over speed. So my time, I'll just say when s is 40, t, which is time, is equal to 6,000 divided by 40. So the amount of time in minutes, remember, 6,000 divided by 40 is 150 minutes. And because they're traveling slower, it's taking them longer. And that's how inverse proportion works. The faster they move, which we'll see here, the quicker the quicker they'll go, which is actually the shorter the time. So bigger speed, smaller time. Once again, so we'll do when s is 110, the time is equal to 6,000 divided by 110. So time is equal to 6,000 divided by 110, which is 54 minutes. Well, it's 54.54 minutes, right? but that's not in seconds. We won't go into the seconds now, but if you use the degrees, minutes, seconds button, you can actually get it if you wanted. So I'll do that now. So that's 54.54 minutes, which is the same if you want 54 minutes and 33 seconds. So we know exactly how long it will take. The last part, part C, find the car's speed if it took 45 minutes to travel 110 kilometers. Okay, so what we're doing is we're going to do essentially the opposite. Okay, so we're going to have when t is 45 minutes. Okay, so using that same equation we had before, 45 is equal to 6,000 divided by s. Okay, and the reason why we can put that straight in is because we're looking at 100 kilometers, and you'll see up here it's referring to 100 kilometers, and then here 100 kilometers, here it's 100 kilometers. So that's why it always will work for this situation. Now we want to get s on its own. So you'll remember with trigonometry when we're doing SOHCAHTOA, if you've got the unknown on the bottom of a fraction, you can switch these. Okay, and that's the same for this because it's just working with equations. So I'm going to rewrite that as s is equal to 6,000 all over 45. And then when I type that into the calculator, 6,000 divided by 45, the speed I'm going to be travelling is 133.33 kilometers per hour. Which, if you're going the speed limit in New South Wales, that's speeding. But anyway, I guess, they were probably speeding. Maybe they were going faster, but they got booked. We never know. So just a recap of the difference. So we've got directly proportional, which is as x increases, y increases, like money. But then you've also got inverse proportion like speed and time, where as x increases, y will decrease. Okay, and you can see that with this table here. So as the speed increases, gets a bigger number, the time will decrease. Okay, if you have any questions, don't forget to email me, and now you can move